Okay, so hello guys to another edition of the Concrete Math Seminar Series. So this time we've got Neumann again to talk about a really interesting but different topic, which is called the ubiquity of ADE graphs and the mutation and numbers games. I'll let you take it away.
Thanks, Gardiner. Well, thanks everyone for coming. So my plan is to investigate some remarkable coincidences, perhaps, that are all centered around a certain family of seemingly relatively simple graphs called the ADE graphs. And in the last few decades, actually perhaps in the last century, these graphs have appeared in more and more numerous areas of mathematics. And this quite long thing just to even list them, but I'm going to at least mention. So even platonic solids are somehow related to them. They are very prominent in the classification of simple Lie algebras and groups, intimately connected with reflection groups, sometimes called Coxeter groups, with geometrical systems in higher dimensional space called root systems, and associated lattices in higher dimensions, with SU2 or the quaternions and finite subgroups of that, with theory of quivers, in physics with fusion rule algebras and more generally conformal field theories, in classification of algebras, remarkably also close connections with finite simple groups, the big finite simple groups like the monster group and the Fisher groups, and von Neumann algebras and many other sort of things. And so it's a kind of a celebrated question as to why all these things are happening, and can we somehow explain these things. So this basic program, I guess, was enunciated first clearly by famous mathematician V.I. Arnold in the mid-70s, who said, let's try to explain what's going on here. And a lot of people have been thinking about these things from lots of different points of view. So typically what happens is that somebody studying one of these subjects makes some investigations and some classification, and then they find these graphs here, and then that immediately connects them with a lot of other mathematics. So my point of view that I'd like to explore in sort of a series of lectures is to try to regard the graphs as central or maybe primary objects and see what we can do just at the level of elementary graph theory and associated combinatorics to try to move towards some of these topics. Now I'm certainly not going to be able to relate all of them, but I hope to make some connections in this fashion. So first of all, let's have a look at what are these graphs. So here are the ADE graphs. There's two infinite families, the AN graphs, which are just like a chain of successive nodes. And N always refers to the number of vertices for these graphs. So N vertices all connected to the chain. And Dn is very much the same, except that at one node here, there's actually two branches going out. And then associated also in this family is these three sort of sporadic examples, E6, E7, and E8, which are these things here. So they're all trees, and these are the ADE graphs that are very important objects in mathematics, and probably the most important graphs in mathematics. Okay, we should not mention them without mentioning also some closely associated affine and affine variants called the ADE tilde graphs, and we'll see their role in a second. So these are like sort of modifications of these where you add an extra vertex. The extra vertex here for the AN tilde graphs is up here forming us a little circuit. And that's the only one that has any kind of, that's a non-tree. With D4, we take D4, we add another one there. With Dn, more generally, we take another one there to make it sort of symmetric. And then E6 tilde looks like E6 with another one on top of the short branch. E7 is another one added to the middle branch to make two equal size branches there. And E8 we add the extra one at the long end to make it even longer. Okay, so first of all, can we say why are these graphs special? So even from a graph theoretical point of view, they are interesting because their spectrums are very important. So in graph theory, something called algebraic graph theory, we're interested in looking at basically the adjacency matrix of a graph. If we take the adjacency matrix and regard it from the linear algebra point of view, we can ask for its eigenvalues and study eigenvalues and associate that to properties of the graph. So in graph theory, these ADE tilde graphs are characterized by having their spectrum. The spectrum is exactly 2. So the spectrum of a graph typically is, it's the maximum of the absolute values of the eigenvalues. So lambda I is an eigenvalue for the adjacency matrix, which we'll usually denote by A. Okay, so that's the spectrum of the graph. And these AD tilde graphs are exactly the graphs that have spectrum equals to 2. And that's associated to the fact that there's a special function on the vertices that has the property that the sum of the neighbors is exactly equal to twice the value at the node. So we're going to have to look at these values. So if we put 1s everywhere on the cycle graph, then the value at any node is multiplied by 2, you can get the sum of the neighbors. For D4 tilde, it's 1, 1, 1, 1, and 2. For Dn tilde, it's 1, 1, 1, 1, and 2s on these intermediate ones. For E6 tilde, it's 3, 2, 1, 2, 1, 2, 1. For E7, it's 4, 3, 2, 1, 3, 2, 1, 2. And for the E8 tilde, it's 6. Value 6 at this node. 6, 5, 4, 3, 2, 1, 3, 4, and 2. Okay, so those are like the eigenvalues of the adjacency matrix corresponding to the eigenvalue 2. And so, for example, this 5 is half of 4 plus 6, and this 6 is half of 4 plus 5 plus 3, and so on. So these are the only graphs in the world that have eigenvalues equal to 2, eigenvectors equal to 2 associated to their adjacency matrix. And then these ADE tildes, well, they're characterized by being the graphs whose spectrums SP of x is less than 2. So these, from a graph theoretical point of view, are the characterizing properties of these graphs in terms of their spectra. Every other graph then has a spectrum bigger than 2. Okay, now I want to introduce the mutation game, which is going to be our starting point for trying to create structure from these graphs. So we're going to start with our focus will be on the ADE graphs, but whenever you study them, you're not far from studying the ADE tilde graphs as well. Okay, so we're going to introduce something which we're going to call the mutation game. And it's a fun game to play on a graph. Okay. And once we know how to play this game, then we'll see not just why these graphs come up in a different way, but also that we can build structure. Okay, so that we can take one of these graphs, and by playing the mutation game, there'll be all kinds of structure that we can build, particular combinatorial structure. And the combinatorial structure will support a lot of these more sophisticated things, or some of the more sophisticated things that I mentioned. Okay, so what is the mutation game? So we start with a graph X, and it's going to be a connected, simple graph. And let's define population on X is an integral valued function on the vertices of X. And we'll denote by P of X the populations. Of X. Okay, and we're going to now introduce a game for various vertices. So let's illustrate this game with an example. So suppose that I have a graph. Maybe I'll use an example that I've already looked at so I minimize the probability of making arithmetic mistakes. So let's consider a population on this graph. So we have 4 vertices. And the population is going to be an integer valued function. Let's give the vertices some names first of all. X, Y, Z, and W are the names of the vertices. And the population's values will be -1, 2, 4, and 3. So what we're going to do is we're going to define for a vertex little x of X, we're going to define S sub X, which is going to be a linear map from P of X to P of X. And it's defined this way. So if we have a population P, I'll have the operation acting on the right. P S of X acting on another vertex Y is equal to P of Y if Y does not equal X, X and Y are vertices, and if Y equals X, we get minus P of X plus the sum over all vertices Z of A, Z, X, P of Z. That's if Y equals X. Okay, so this is the all-important definition. So let's see what actually happens. So what we're doing here is we're going to call this mutation at X. So I want you to think about this population as representing Martians. Okay, these are cities on Mars. These are cities on Mars, and these are roads that connect the cities. And on Mars, there are 2 types of Martians. There's Martians and anti-Martians. Okay? And if you put a Martian and an anti-Martian together in the same city, they mutually annihilate each other. So any city either has only Martians or anti-Martians, or maybe nothing. So this -1 represents this one anti-Martian here. So every so often, a city may mutate, which is one of these operations. And when a city mutates, what happens is that all the other cities, nothing happens to them. But the city that mutates, all the inhabitants turn into anti-inhabitants. And to deal with this mutation, all the directly neighboring cities clone their populations and send them into the mutating city in order to cancel out the mutation. So for example, let's see what would happen if we took this population. Let's call it P. That's population P. And let's look at what happens if we take P and we apply the mutation S sub X. Okay, so we're going to get what? So first of all the other population values are maintained. And what happens at here is the -1 changes into a +1. And correspondingly, all the directly adjacent neighbors, which is only this one, sends a copy of their population to the clone thing. So we get a -1 plus a 2 for a total of +1. That's the effect of the mutation S sub X on this population. What would happen if we took the same population P and applied S sub Y? Well, then we would get what? So S sub Y, mutating there, we get -1, 4, 3. That's not going to change. But the 2 is going to change into a -2. This 2 is going to go into a -2, and then we have to add a copy of all the directly adjacent populations, which is -1 plus 4 plus 3, so for a total of, I guess, 4. And if we did S sub Z, then we would get -1, 2, 3, and 1. There. And if we did S sub W, we would get -1, 2, 4, and 3. In this case, the 3 doesn't change, even though we're mutating there, because we take the original and we take 3 and make it negative, get -3, and then we add a total of 6, and we're back to 3. Yes?
That first example of being a 3, because it was -1.
1 minus 1.
Oh, you're right. Absolutely right. So the -1 changes to a plus 1, thank you. And then we add 2. Yes, thank you, Daniel. That should be 3. One way of checking that one hasn't made a silly mistake like this is to verify that when you take any reflection and you square it, you get the identity. If you do it twice, for example, if we do it twice now with this corrected value, if we took the 3 and we made it into a -3 and then we added 2, we would get back to -1. Another relation that's kind of obvious is that if the two cities are not adjacent, then the reflections commute. So S sub x times S sub y equals S sub y times S sub x if x and y are not neighbors. And what if they are neighbors? Well, then something more interesting happens. So if x and y are neighbors, then we get a braid relation. We get S sub x, S sub y, S sub x equals S sub y, S sub x, S sub y. This relation, if you're familiar with the symmetric group, it's the kind of thing that happens there. So these 3 are the main sort of relations in the group generated by the reflections. We can now consider the group because all of these are invertible because their square is the identity. So we've got invertible transformations acting on this linear space. And we have then a group, and we could call the group something. So we could, let's say, W be equal to the group generated by all these reflections. Group generated by S of x, where x is a vertex of x. That might be an infinite group, or it might be a finite group. At this point, we don't know. Yes?
As you may know, there's recently been a lecture series on cluster algebras.
Cluster algebras.
And so mutations are there. But now I don't know enough about the history of all this to know, is the idea of mutation a standard thing in graph theory?
Not that I know of.
So is this coming from also the Zelevinsky?
No, I mean, this is it's like kind of a restatement of ideas that are quite familiar in the theory of Coxeter groups and Weil groups. It's kind of taking ideas from there and sort of stating them purely in graph theoretical kind of fashion. Okay, so now we understand what mutations are, and so what is the mutation game? Well, the mutation game has an objective, at least a vague objective. The objective is to create big populations, starting from small populations. Same as the objective of most countries in the modern world. At least most governments. Okay, so what's the mutation game? So you get to start with a singleton population, very modestly. Start with a singleton population. Let's call that delta of x. And that means 1 at x and 0 elsewhere. And then what you try to do, then try to get a big population by carefully, randomly making a sequence of mutations. By a sequence of mutations. Okay, so let's demonstrate this with an example, a famous one, E6. So the graph E6 is just a remarkable thing. It's connected, amongst many other things, to the 27 lines on a cubic surface in algebraic geometry. It's important 19th century drill. So it turns out E6 is associated with that and lots of other things. So let's play the mutation game on E6. So we'll start with a 1 somewhere. And the first thing I want to convince you is that it doesn't really matter where we put our singleton. So I'm going to do that by showing you some simple mutations. So if we start with the singleton here, and whenever there's nothing, you assume there's 0 there. So if we say mutate here, what's going to happen? You're allowed to mutate an empty city. The rule is still the same. So the 0 here turns to -0, and then you have to add the neighbors. So you're going to get a 1. Mutate here, 0 turns to a 0, you add a 1. And let's say then after that we decide to mutate here now. This 1 turns to a -1, we add a 1, that's going to go to 0. And then if we mutate here, the 1 turns to a -1, and now we add only 1, so that's going to turn to 0. So the net effect is that we've gone from a singleton here to a singleton here by a bunch of mutations. So you can get from any one singleton to any other singleton by mutations, so it doesn't really matter if you're trying to build up a big population, which singleton you start from. Okay, so let's start, let's say, here, and let's try to build a population on E6. Okay, first of all, if we mutated here, let's just observe what happens. If we mutated at the vertex where we have a 1, then that would change into a -1 and nothing else. And then any subsequent populations that we got would just be negatives of any ones that we're going to get with this one. So there's going to be a symmetry. There's going to be a symmetry in the world of populations that we can get to just by multiplying by -1 due to this basic symmetry at a singleton. Okay, so let's not do that because we're interested in big population, positive one. So let's mutate here, we get a 1. 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 Okay, now we could mutate at another place. If we mutated here again, that 1 would just disappear, then we would be going backwards. If we mutated here, we would get -1 plus 2, which would be 1. It wouldn't do anything for us. It would not change. The only thing that's going to move us forward is mutating at this vertex here. At that would result in what? That 1 would become a -1, and then there are 3 neighbors, so the -1 plus 3 is 2. So we can jack this up to a 2. Now if we mutate here, things are a little bit different from what they were previously. Now it's -1 plus 3, which is 2. So we get a 2. And similarly, mutating here gives us a 2. And now, if we mutate at the central spot again, we get a -2 plus 5, which is 3. So we can get 3. And then the only thing you can do to increase things is to mutate here. -1 plus 3 gives you a 2. And at that stage, no more mutations are going to increase the population. You've achieved the maximum population for this configuration of cities and roads on Mars. That's the maximum population, which you will see is pretty close to this eigenfunction of the adjacency matrix that we mentioned for the affine variant. Okay, so now there's a theorem, but to tell you what the theorem is, I'll just introduce a bit of notation. So we'll say that a root population is a population obtained from a singleton by successive mutations. And we'll let R of x be the set of, or the type of, root populations. Okay, so now we can mention a theorem. Theorem is that the number of elements in root population, in other words, the number of different populations that you can get by starting with a singleton and performing arbitrary mutations, is finite. It's finite precisely when X is an ADE graph. So you could discover the ADE story by playing this mutation game. If you have any other graph, there's an unbounded number of populations. You can get as big a population as you want. But just for these, there's a maximum population. Okay? And the maximum population plays a big role in Lie theory. And so let me tell you what the maximum population is. Here it's all ones. And then here it's 1, 1, 2, 2, all the way to 2, and then 1. Jay, you can correct me if I'm making mistakes. 1, 2, 3, 2, 1, 2. That's the one we just got. 1, 2, 3, 4, 2, 3, 2. Is that right? 1, 2, 3, 4. No, that's not right. It's got a 6 here. Oh, I'm sorry. It's got a 6, 5, 4, 3, 2, and same 2, 4, 3, I guess. So these are maximal populations. Okay, so I want to explain to you how one proves this theorem. So the key is actually to consider the ADE tilde graphs first. So the proof idea. The proof is, first of all, to show that R of x is unbounded. I'll use that notation. If x is an ADE tilde graph. And the way you do that is by performing an explicit sequence for the E6 one. So let me, for those ones, let me illustrate the argument. So you have to work through all of them, and you have to do computation that looks something like this. So for E6 tilde, so it's like this. Let me convince you that you can get an unbounded population for E6 tilde. So we'll start with 1 here. It doesn't matter where we do it, we perform mutations. I'm going to do the same kind of thing as I just did previously. I can do it fast now. There'll be 2, it's 2 hands, and then I can make these ones 2s, and then I can make this one to a 3, and then I can make this one into a 2, and then at this stage I could. I haven't used this one here yet, but I have an extra one that I didn't have in the previous story. This is the extra affine vertex. So I can use this one now, I can mutate here, and that'll give me a 0 plus 2, that'll give me a 2 there. And then what?
You can get a 3.
And then I can get a 3 here. And then I can get a 4 here. And then I can get a 3 here. And then I can get a 3 here. And then I get a 2 here. And I get a 2 here. And you can kind of see the pattern. But if we wanted to be more precise about it, we could say that this thing here that we got is exactly the same thing as we got a minute ago, plus this eigenvector of the Perron-Frobenius eigenvector. And the crucial property about this one here, at the level of mutation games, if you play the mutation game on this particular population, is that it's unchanged by any mutation. The definition of mutation game is exactly that if you take minus this one and you add twice, add the neighbors, you're going to get back to where you started. So this is constant on the mutation game, and that means that once we've added one of those things, added one of those to the initial thing, it's going to stay there upon successive mutations. And so then when we go through the sequence again, then we'll generate another one of those Perron-Frobenius ones, and then we'll generate another one. So we can just keep on basically jacking up the number of Perron-Frobenius vectors by going through the same sequence. So it's really the existence of the Perron-Frobenius vectors over here, and the fact that they're stable under the mutation game, that allows us to relatively easily verify that for the ADE tilde graphs, there's an infinite number of vertices, an infinite number of root populations. And then you observe, second observe, is that if a graph, if X contains an ADE tilde graph, then R of X is also going to be infinite. If a graph contains E6 as a subgraph, then you can just play the mutation game on the subgraph and you get an infinite number of populations, so you can get an infinite number of populations for the bigger graph. So then you only need to worry about which graphs do not have an ADE tilde graph inside them. Okay? So then you have to convince yourselves that exactly the ADE graphs don't have ADE tilde graphs as subgraphs. That's kind of obvious, because we created the ADE graphs by starting with ADE tilde graphs by starting with the ADE graphs and adding stuff. And then you have to check that for each ADE graphs, the number of things is actually finite. You check finiteness. Check R of X is less than infinity for the ADE graphs. Now, this kind of classification scheme, this kind of argument, is parallel to dozens of other arguments in mathematics. Okay? So there's lots of places where the ADE graphs figure, and there will then be an argument that looks more or less like this, in some fashion or another, that somehow related to the classification of the ADEs that are appearing. It has similar kinds of features. So once you've seen one or two of these arguments, you kind of get the hang of it. So that's a quite nice fact that identifies for us that these ADE graphs are interesting, and that this mutation game somehow is connecting and somehow maybe expanding on the eigenvalue property of the ADE tilde graphs, and actually giving us some more piece of information about these things. And so now, the natural question is, how many of these roots are there? Well, maybe you could just pass this one. So this is some kind of handwritten copies of what the AD, what the the E6 roots look like. So it turns out that if we're talking about AN, then the number of elements in the number of roots for AN is n times n plus 1. For Dn, it is 2n times n minus 1. For E6, it is 72. For E7, it is 126. And for E8, it is 240. So these are kind of like the root systems, classical root systems, which I'll explain in my next lecture, probably, what a root system is and the connection here. But I want to tell you another remarkable fact about these root populations that is actually, I think, a very deep and important problem in graph theory. Sorry to rub out the stars here. So to tell you this other important fact, let me just establish that for me, x is greater than or equal to 0. That's the same as saying that x is positive. And if x is greater than 0, I'll say that means that x is strictly positive. Okay, so I'll use those. If x is less than or equal to 0 is negative. And so on. Okay, so let's introduce the positive populations. So these are the positive populations. So these are just the populations P in P of x, such that P of x is greater than or equal to 0 for all vertices x. And similarly, we'll denote by P minus x the negative populations. And now let's define, so we've defined the root populations, all the populations that we can get to by using the mutation game. Let's define R plus of x to be all the roots which are positive, the intersection with P plus of x. So these are the populations for which there's no anti-Martians. And similarly, R minus x will be R of x intersect P minus of x. So in this case, no Martians. Only anti-Martians, or possibly zeros. Okay, so now here is, it's a kind of a theorem, but it's theorem conjecture. I'll explain that in a second. Theorem conjecture, that for any graph x of the kind that we're considering, that is connected simple graph, the root populations are always either positive or negative. What does that mean? So it means that there are no populations that you can get to from a singleton population that have both strictly positive and strictly negative elements. I.e., no root populations with both Martians and anti-Martians. So for example, that first thing that I showed you, this population I had a -1 here, and maybe there was a 2, 4, and 3. This one here is not a population that you can get to from a singleton using mutations. No matter how clever you are. There's an infinite number in this case, because this is not an ADE graph, so there's an infinite number of populations you can get to, but this is not one of them. It's not one of them. Every population is either all positive or either all negative. Now, why is this a theorem and a conjecture? Well, I happen to know, because of conversations that I've had with Bob Howlett at the University of Sydney quite some time ago, that this is a consequence of reasonably sophisticated results in the theory of Coxeter groups. So there's an algebraic proof of this. Bob Howlett convinced me of that, although I wouldn't be able to recall what that argument was. But it's a conjecture in the sense that I don't have any graph theoretical or combinatorial understanding of this. This is a situation where you're playing this game and something's always positive. So it turns out that if you start with a singleton, anywhere, it doesn't matter where, you start with a singleton and you agree never to perform a mutation at a singleton. That's a way of getting a negative. If I perform a mutation at that vertex there, that 1 will change into a -1. If I agree never to do that, I will never perform a mutation on a poor singleton, then the theorem is that I can never get any negatives. I will be forever forbidden from getting any negative entries. Even though I'm always mutating, I'm getting something that's negative, at least temporarily, and then there's the effect of the neighboring things to cancel out, and that neighboring effect is always effective, no matter what graph you start with. So I would love there to be a combinatorial proof of this. A combinatorial proof because it's basically a positivity, so there should be some kind of graph theoretical or combinatorial counting that somehow underlies it, that generates the result, but I don't know how to do such a thing. But I believe that a proof, a combinatorial proof, would be very instructive and would shed probably a fair amount of light on a lot of the topics that are sort of connected with the AD graph. So no combinatorial proof known, at least by me. Please.
Sorry, so the game is again that you're building things from a singleton, that's all.
That's always our starting point, that's right. We always start with a singleton.
Okay, so I mean, is there results for mixed Martian, anti-Martian, because you can just start.
You can start with
mutations?
absolutely. I have no idea.
Uh-huh.
I have no experience of what happens, or what kind of populations you get if you start with some arbitrary, non-singular thing. In fact, I don't even have much experience with what these root systems look like for non-ADE or non-ADE tilde graphs. If you just choose a general graph and say, what are all the possible root populations that you can get? If it's not ADE tilde or ADE, we know there's an infinite number of them, but characterizing them or describing them, I have no idea.
This reminds me all of cellular automata and all sorts of ways of building rules.
Yeah, it's very concrete, but each step is simple, but the cumulative situation of where you end up is not so easy to describe. Okay, since I only have a few more minutes, I'd like to finish by drawing your attention to this E8. Okay, so E8 figures in another way that's not on the list of original things that I said, because the physicists have a theory. There are many theories in physics, but one very appealing one is that E8 is somehow connected with a grand unification of all fundamental forces. That the base symmetry group of the universe is somehow the E8 symmetry group. And this is a very intriguing proposal, which I don't know that much about, but I'd like to know more about it. The E8 here is only a graph, but it turns out there's a Lie algebra, Lie group, and the dimension of the E8 Lie algebra is 240 plus 8. which is 248. And so that's a very interesting thing. And another interesting thing is that E8 turns out also to be connected to the monster group. The monster group is the biggest of the sporadic simple groups, which Peter will know about. But somehow there's some remarkable connection also between E8 and the monster group. So we're touching base here, at least at the numerology level, with lots of interesting things, and kind of like to know what's really going on here, but we're not alone in that. A lot of people would like to know. So in our next lecture, I want to explore a little bit more about the root system aspect of things, and then sort of connect where are the Lie algebras floating around here. That's a very interesting question too. So thanks.
All right, that was a good talk, Norman. Any questions, comments?
Yeah, I think I missed what the and or operations mean for px and rx.
And or,
Yes.
which ones?
So when you write rx is equal to r plus x, or
the function, mutation.
Oh, so Rx is a set of all root populations that you can get.
yes, and there's a binary operation that looks like an and in between rx and p plus.
It means the intersection.
Oh, this intersection?
Yes.
Just the intersection, so the things that are both
Yes, yes.
roots and have positive entry.
This graph here means simply laced, only one edge allowed between any two vertices.
Yeah, so this is all the simply laced version. So there's another aspect of this story, which is the non-simply laced, where the ADEs have to be augmented with the F4 and G2 and Bs and Cs.
But if you want to study mutation games in that context as
The
well.
mutation game turns out to also work in that situation. And the situation is quite parallel, but it's a little more sophisticated.
What's a good reference for this, Norman? I mean, where is this dating from?
Well, I wrote a paper on this many years ago, which I never completed and it was never published. So there's not really a good reference that I know of. But the underlying things, there's on ADE graphs more generally, there's lots of information, there's lots of survey articles. There's even a book with a title of something like The Ubiquity of ADE Graphs, Hasewinkel and other co-authors. So there's a lot of information generally in the world about this. It's a very interesting topic. But this mutation point of view is my own little sort of way of thinking about things. So. Yes?
Is the finiteness of the root population in the literature somewhere?
Oh yes, so that'll, that's intimately connected with the theory of Lie algebras, and the root systems there play an important role in terms of the structure constants of a simple Lie algebra, and so that this is all, at some level, this is all well documented at the level of Lie algebras or Coxeter groups or root systems. So either any of simple Lie algebras, root systems, Coxeter groups, maybe even quiver representations of quivers will arise at the basics, the same kinds of combinatorial objects.
Yeah, sometimes you can use a quadratic form to see if the quadratic form is positive, definite, positive, semi-definite to classify this.
That's right, yes. The quadratic form, as Jay mentions, is behind the scenes here, and I'll be talking about that probably next time as well. Yeah. Peter?
Yeah, my memory is fading, but I think Hasewinkel did have the first paper with the word ubiquity in it in the mid-70s.
Before Arnold's?
May well have
Maybe.
sometime like that.
In the mid-70s, okay. So the suggestion is a paper by Hasewinkel in the 70s that has this point of view in it also.
You talked about the connection of the dimension of the Lie algebra E8
Yes.
the root system. What about the other ones?
It's the same story. So if you, the dimension of E7 as a Lie algebra is 133. The dimension of E6 is 78. you add the index to the number of roots, and that corresponds to some classical decomposition of a Lie algebra into a Cartan subalgebra and space and
That works with
root
the
spaces.
That works with the A and D.
Yes, it works for all of them.
Another thing that didn't happen in the mid-70s was you could have picked up what non-commutative geometries had to be from the tilde graphs. They had to wait for Alain Connes rather later.
Yeah, so that would have been one. Another development would have been the Kac-Moody story, which I think, when did the Kac-Moody story appear?
7 days, I think.
In the 70s also, when
60, 70.
the sort of Lie algebraic analogs of the affine algebras sort of entered the stage and expanded the subject quite a lot.
Anyway, bits of Connes could have
Bits of
been
Connes.
done from this. Not all of him, of course.
Any other questions? At the end of this point, just one more round of applause for Norman.